Hello, everybody. We start the session. We start the session 5A. The speakers have a 15-minute talk and about 3 to 5 minute Q&A. I'll let the speaker the 3 minutes before the end. And the audience can ask a question through the Q&A menu, please. Okay, then the first speaker is Sung-Young Kang about the WimPyDD. Please share the screen. Okay, then let's start the session. Let's start the talk, please.
Thank you for your introduction. Hello, everyone. This is Sung-Young Kang from Sogang University. Today, I will introduce WimPyDD, an object-oriented Python code to calculate WIMP direct detection signals. Okay. Let me start with basic concepts. As you know, around 23% of the total mass density of the universe and more than 90% of the halo of our galaxy are believed to be composed of dark matter. And WIMP, weakly interacting massive particle, is one of the most popular candidates. It interacts in weak scale with ordinary matter and can provide the correct relic abundance. Therefore, worldwide experimental effort is underway to detect WIMPs. And in direct detection, the signals are nuclear recoil events and result is detection rate. Usually the detector is located underground or shielded artificially to avoid background. And each experiment has different setups, so it's not easy to handle various data. Therefore, I introduced WimPyDD, object-oriented and customizable Python code that calculates accurate predictions for the expected rates in WIMP direct detection experiment within the framework of Galilean invariant, non-relativistic, effective theory. WimPyDD handles different scenarios, including inelastic scattering, WIMP of arbitrary spin, and a generic velocity distribution of WIMP in the galactic halo. WimPyDD is written by our lab members. Before its present release, WimPyDD has already been tested and presented results such as these papers here. And, main features of WimPyDD is, once again, object-oriented, customizable, and also portable, being based on Python. And it can calculate expected rates in WIMP direct detection in any scenario such as listed here, including the detector's response. The way to do that is calculating these three main components, Wilson coefficients of the effective theory, the detector response functions, and the halo function, and stores them for later interpolation using a parameterization that does not depend on WIMP mass. Therefore, WimPyDD is transparent and fast, suitable for WIMP parameter space of large dimensionality. This is a whole structure of WimPyDD. Especially, it provides three routines to calculate expected signals: d sigma DER, diff rate, and WIMPDD rate. You can easily install this WimPyDD. Just go to the home page and download zip file or Git in your working directory. Now import WimPyDD with a simple command, and all libraries are standard. To test the installation, just use test WimPyDD installation file we are providing, and it will automatically execute simple calculations and produces some plots. Three main routines calculate the differential cross-section on target, differential rates, and integrated expected rates each. In order to do that, 4 Python class inputs are needed. First is element class. Some of them are predefined. And second is target, a single element or linear combination of elements. Next is EFT Hamiltonian, where two operator bases are available according to these two papers. Last one is experiment class containing setup information. From here, I will explain more details with examples. First example is differential rate on sodium iodine for standard spin independent interaction. In this case, we need Wilson coefficients, target class, Hamiltonian class, model parameters, and Hollow functions. At the beginning, we can set up Hamiltonian using class named EFT Hamiltonian. This is a Python dictionary with operators and Wilson coefficients. Here, I put 1 for dictionary key to choose operator O1, where 1, 3, and up to 15 is available. Wilson coefficient is a value of dictionary, which is needed to be a function of arbitrary parameters, including transferred momentum. Finally, this routine, EFT Hamiltonian, gives an Hamiltonian object. In terms of operators, two bases are available. One is seen in the table, only can be used when WIMP spin is smaller or equal to 1/2. The other is in this notation at the right, where X indicates nucleon current, S the number of WIMP spin operators, and L the power of the momentum exchange vectors. This notation can be used for arbitrary spins. Next step is to set up Hollow function using streamed Hollow function routine, whose default setting is Maxwellian with standard choice of the parameters. The result of that is an array containing velocities and Hollow function. For instance, can show a plot like this. Also, this streamed Hollow function routine works for a generic velocity distribution. And then one needs to set up the target. Notice that quenching factor is a kind of experimental input. So in order to include quenching, it should be an attribute of an experiment object, which I'm going to explain a little bit later. For instance, in this way, now this NAI is an attribute of DAMA and has DAMA quenching factors. Of course, there are experiments which uses same targets, but different quenching. In this case, we can distinguish assigned to the other experiment. For instance, to use different quenching for cosine, just type NAI is equal to cosine the target. But if not assigned, there will be no quenching information. And when target is a compound, just taking linear combination is enough. Last procedure is to call diff-rate routine. Here, this M is passed. This M is passed as keyworded variable length argument. And here is a result. In this plot, sodium and iodine is calculated with different quenching. In addition to that, this plot contains results including detector's response. How to include them, I will show you in next example. Now we can calculate bind rate on sodium iodine for same Hamiltonian, including detector's response. In this case, we need Wilson coefficients, Hamiltonian, experimental information, response functions, and Hollow functions. First of all, one can set up experiment class using command like here. The name of experiment is needed to be passed as a string in order to indicate the directory inside of WimPyDD folder properly. There, detector information such as energy resolution, energy binning, exposure, quenching for each target element, and the information of targets such as formula is located. The format of their files is a Python function or table to interpolate. And then one need to load response functions using below command. Calculation of rate requires double integral, so it's slow. However, WimPDD performs calculation independent on WIMP mass only at first call, and later just loads pre-calculated response functions. So it can be very fast. Next is to call WIMPDD rate routine, including also the keyword arguments. And now you can see the result with response of detector. And one of the main features of DAMA experiment is that yearly modulation is concerned. WIMPDD can calculate this too, for instance, with Hamiltonian 09. As I mentioned, EFT Hamiltonian class needs Wilson coefficient as a function. So we need to define it first in this way. It returns two couplings, C90 and C91, calculated in terms of three parameters, WIMP mass m chi, and sigma p, and the ratio are defined like here. And then we can set Hamiltonian class as same as before. Considering yearly modulation, one needs to put one parameter, yearly modulation is equal to true, to get Hollow function for modulation. Then load response functions as before. Last step is to call WIMPDD routine, including keyword arguments. And here we can easily get the result. WIMPDD can handle more complicated Hamiltonian, such as 04, 5, and 6. This Hamiltonian is in terms of 8 parameters, m chi, sigma, delta, and this C0 vector. This C0 coupling vectors can be expressed in terms of an effective cross-section, parameterizing the coupling's intensity, sigma f. And here, this EFT Hamiltonian class may look difficult, but it's in the same structure as before. Then we need the values of keyword arguments. Using them, one may call WIMPDD routine, putting inside these values in the routine. And here you can see the result. And then the exclusion plot can be easily obtained too. WIMPDD provides the routine m chi vs exclusion to calculate exclusion plots. Setting up.
We have 3 minutes.
Yep.
We have 3 minutes, please.
Okay, I see. Thank you. Setting up Hamiltonian and experiment. One may call this routine. Okay, so setting up experiment like this, and one may call this routine. Then it will provide an exclusion plot. Okay. Yeah, I couldn't explain all the details here, such as implementing new targets using custom nuclear response functions. So default choice is based on these two papers. Arbitrary velocity distribution using modifier to allow for additional effects, and estimating the upper bound on any parameter using this m chi vs exclusion routine. So I'd like to say, please visit homepage for more details, and thank you for listening to me.
Thank you. Okay, please, any question and discussion? No question yet. And may I have just one question? Yeah.
Yes.
Does your code have the database for the older experiments, including the target material or etc.?
Yeah. At the beginning, now we are providing kind of example through our homepage. We are providing DAMA and Xenon and Pico experiments using all the ingredients. I mean the experimental setup. And if you want to set up new experiments, then there is a folder named WimPDD, and you can put those ingredient files in that proper directory, and then use these code as I told you.
but the experimental group should provide the information, right?
Yes, and yes.
Please do. I see. Okay. Any other questions? Okay, you keep the time limit very well. So, and thank you for the interesting talk. Thank you.
Thank you.
Okay, the next speaker is Alice Kay about the dark sector in the ATLAS detector.
Hi. I'm not
Okay.
sure if you can see me. I think my webcam isn't working. But okay. Oh, maybe you can see me now.
Okay.
So I'll try and share my slides.
Yeah.
Okay. Can you see the slides?
Okay.
Right. Great.
Okay. Then let's start the talk, please.
Okay. So good morning. Good afternoon. I'm going to be talking about the dark sector searches that are ongoing in the ATLAS detector. So I'll start straight away. The idea is that new physics like dark matter might exist in some hidden sector or dark sector, which is composed of particles which don't undergo standard model gauge interactions. And then maybe they could couple to the standard model through some sort of mixing term in the Lagrangian. So they could communicate through standard model mediators or dark sector mediators, which could be themselves dark matter candidates or could provide so-called portals to the hidden sector. And the portal relevant to this hidden sector will then depend on the properties of the mediator, such as the spin and parity. So we could have vector, scalar, fermion, pseudoscalar portals. So you can see a little sketch on the left where we have the standard model and then a hidden sector, which could have new physics like a new U1 symmetry. And there's a communication via the Higgs boson to a dark scalar. So because of the limitations with the gauge and Lorentz symmetries of the standard model, there are limited ways in which this sector can communicate with the SM. And this could often lead to unconventional signatures, which we see at our experiments at the LHC. And that's what I'm going to focus on in this talk. There are a lot of other types of dark matter searches, including MET plus X, and I think my colleague from CMS is going to talk about those tomorrow. So I'll just have a very brief introduction to what the ATLAS detector is. It's one of the 4 main detectors at the LHC, and it's a general purpose hermetic detector. So it's designed to detect as many different signatures as possible and to try and find all of the particles coming from the interaction point at the very center. And it consists of different types of technologies in layers coming from the center that are supposed to detect different particles. So we have the inner detector for charged particle tracks, the electromagnetic and hadronic calorimeters for the energy of photons and jets, and then the muon spectrometers to get the muon tracks at the far edges of the detector. And another notable feature is that we have a two-level hardware and software trigger, which reduces the 40 megahertz bunch crossing rate of the protons to a manageable data rate of 1 kilohertz. So now if we just look at a cross section of the ATLAS detector on the right, I want to show what some of these unconventional signatures can look like. And in particular, if we have weak couplings to the standard model, then this can lead to long-lived particles, which themselves can give a lot of these unconventional signatures. So as I mentioned, the ATLAS detector is designed to look at prompt decays from the center of the detector. But with these long-lived particles, we could have decays happening really far out in the detector, and this might come with new experimental challenges where we have to use special triggers or tracking or look for timing information, which we don't necessarily have in all of the detector. So we're using ATLAS in ways that it wasn't designed for. Now I'll just describe some examples of some different analyses we have been performing quite recently. So first, an example with a dark photon case. So this looks at a U1 extension of the standard model, which introduces a new dark photon that mixes kinetically with the standard model. And in this benchmark model, you can see depicted on the bottom left, there's two scenarios. The Higgs decays to a dark fermion pair. And in one case, it decays to a lighter dark fermion, which is presumed to be the hidden lightest stable particle, and a dark photon. And in another case, it's a dark photon pair coming from a dark scalar. And so if we look on the right at the sort of branching fraction for dark photon decays, at low masses, the decays to leptons are prominent, and this is what this search looks at. So the signature in the detector is highly collimated groups of leptons, which we refer to as lepton jets. And this is a nice distinct signature in the detector. And depending on the mixing or the kinetic mixing parameter that we choose, we can have prompt or displaced lepton jets that we look for. So unfortunately, we didn't see any excess over the standard model in this search, but we set limits on the branching of the Higgs and the mass of the dark photon. And here what I'm showing actually is they're interpreted in the case of the mixing parameter. So first, if we look at the plot on the right, the shaded colored regions represent different Higgs branching fractions, and these are the excluded areas in the dark photon mass and the mixing parameter. And the dotted line here is the same result from the run one search. So you can see the general improvement over most of the dark photon mass range. And also in run one, there was a prompt search as well for shorter lifetimes, and you can see the complementarity there of the results. On the left, this is actually the run one search on this plot because we don't have a summary plot yet for the latest result, but we compare this to various fixed target and beam dump experiments. So you can see how it's complementary in its coverage of the dark photon mass and mixing parameter space. Now, another example, this time with a Higgs portal, and this result actually is a prompt search. So there are two scenarios considered. One, where the Higgs decays to a standard model Z, well, two standard model Zs, but one of them couples to a dark Z. And then we have a 4-lepton final state in the detector. And you see that we have this mixing between the Z and the dark Z. And in the other, the Higgs actually interacts with a dark scalar with a mixing kappa and decays this time to 2 dark Zs. And in the second case, there are 2 mass ranges considered, where in the lower mass region, we only look at 4 muon final states. So we actually look for 2 dilepton pairs and then couple these together for a 4-lepton set. On the left, you can see in the hypercharge case, this is the mass distribution for the subleading dilepton. So the data is the black points, and we have various backgrounds in the different colors, where the biggest background is Higgs to ZZ. And we have some different signal mass points shown as well. And then on the right is a similar plot for the Higgs portal case. But this time, instead of just looking at the subleading dilepton, we have a mass which is averaged over the 2 dileptons. And you can see that there are very few events surviving the selection here. And I'll just show, again, we don't see any excess. Oh, I think my slides are frozen. There you go. Over the standard model, but we set constraints on the branching fraction of the Higgs to the Zs and the mass of the dark Z. So these are upper limits on the left for the hypercharge portal. And on the right, it looks a bit different. There are these grayed out areas, and those are vetoes, because we can have some quarkonia resonances where the Higgs can decay to a J psi, so we cut those out. And strikingly, you might see that there's a jump in this limit, and that's just what I mentioned, where in the higher masses, we add the electron channels, and this gives us a boost in sensitivity. So we've had displaced lepton jets, but this time I want to talk about displaced hadronic jets. So yeah, there's a couple of results that I reference in the top here, and here are the sort of models that they consider. For example, we could have a long-lived scalar, which decays to 2 scalars and then to 4 fermions, which if we consider that they follow Yukawa couplings, and they would be heavy fermions. Or we could have a similar case where we have a Higgs decaying to 2 singlets, which is a dark Higgs coupling to a standard model Higgs. So I've already mentioned the scenarios of these long-lived decays, but I just want to mention how we actually apply those experimentally. So for example, if we have a decay that's in the inner detector but occurs far away from the interaction point, or a decay that only happens all the way out in the muon spectrometer, we call these sometimes MSID searches, and these might require dedicated tracking algorithms, which rather than looking at tracking all the way from the center, look at muon only tracking or tracking later on in the ID. Another case, we could have particles that decay in the middle of the calorimeters or even on the edge between them. And in this case, we could have larger deposits in the hadronic calorimeter than in the electromagnetic. And these are often called cal ratio or CR searches, and they have dedicated triggers available to look for this ratio. So again, the 3 results I show set limits in the branching fraction and the proper lifetime, this time of the long-lived particle. And I show these 3 results here, but well, I'll first say that this is the ID and MS search. This is a search for displaced vertices, either 2 of them in the muon spectrometer or 1, and very little activity elsewhere. And this one looks for this cal ratio, so decays mainly in the hadronic calorimeter. And if we focus on the plot on the left, this is the newest result. So the green line is for this analysis, and it's looking at these ID displaced decays. But then the purple line actually is a combination of these 2 other results here. And then if you combine both of these again together, you get this blue limit. So you can see that how they complement each other and give us stronger limits. Now, I didn't go too much into the details of those because I'll show a bit of a newer analysis here on a similar vein. So again, this looks at an exotic Higgs decay, which can be hard to trigger if we have Higgs to 2 axions. But here we're looking at associated production with a Z decaying to 2 leptons, and this gives us a nice dilepton pair to look at in our final state signature. So the signature will be 2 leptons and also a displaced vertex in the inner detector. And this uses what I mentioned, this dedicated tracking. It's referred to as large radius tracking. So it's similar to our normal tracking algorithms, but it has looser restrictions on especially the impact parameters. And also it uses secondary vertex reconstruction that is optimized for long-lived particles. And in this search, we have the 2 displaced vertices, but they actually use 2 control regions to calculate the backgrounds. So you can see on the plot on the left, one of the control regions is requiring 0 displaced vertexes, and the other one is requiring 1. And so the third bin in this plot of number of displaced vertices is the signal region, and actually 0 events were observed in the signal region. So limits were set again on the branching fraction of the Higgs, this time to the pair of pseudoscalars as a function of the mean proper lifetime. And here the middle curves, the orange and blue and gray, represent this analysis for different masses of the pseudoscalars. And on the right actually is a curve coming from the cal ratio and muon analyses that I showed in the previous slide. So again, they're covering a complementary range of the lifetime, and this result actually gives the most stringent limits in this regime for masses of the pseudoscalar below 40 GeV. Now
Okay.
I've talked.
We have 3 minutes.
Oh, okay, I'll try and hurry. So we've talked about vectors and pseudoscalars. This time is a new fermion analysis, so it's looking for a new right-handed neutrino, which is quite sought after. It could explain the neutrino masses and other outstanding questions. So it looks at different decays, which could be lepton number conserving or violating. So the final state signature is 3 leptons, either of the same flavor or 2 of the same flavor and 1 different. And they look at the prompt and displaced regimes. On the bottom left, you can see a selection efficiency for Monte Carlo in these 2 regimes. So the black is for a 10 GeV neutrino in the prompt selection, and the displaced selections are shown on the right for different neutrino masses. Again, limits are set on the coupling this time strengths. So that's this U for the prompt and displaced cases. So the prompt is shown here in this line. Everything above this line is excluded, and the displaced is in this ellipse. The lepton number violating is the full line, and the dotted is the conserving. So one more analysis I want to show, just for the diversity of our physics, is because we don't just use proton beams, we also look at lead beams. So here is an example of a search for an axion-like particle in light-by-light scattering. We treat the lead nuclei as a beam of quasi-real photons, and so we could have an axion produced decay into 2 photons again. And you can see on the left, we plot the diphoton mass. You can see a signal in red and the data in black. And this is used to set limits on the ALP mass. You can see on the right, the blue is the exclusion in the coupling to the axion for this result, and CMS in green. And this is compared to various other experiments, again, showing that we're given a complementary coverage. So I don't think I've got really time to read out my conclusions, but yeah, I just wanted to highlight that we have quite a diverse program at ATLAS for unconventional signatures. And there's also a lot of potential. A lot of these analyses haven't looked yet at the full run 2 data. And from March next year, we'll be having run 3, even with some upgrades on our detector. So yeah, hopefully we'll continue to push into this dark sector. So thank you.
Thank you. Any question and comments? Okay, I have just a simple question. You use the heavy ion data for the axion-like particles, right?
Mm-hmm.
And, could you explain the reason why not the proton data but the heavy ion data?
Well, we use the proton data for all of the other searches, but in this case, I mean, this is just where we've considered that we can have these photons coming from the heavy ions, and the light-by-light scattering is just one of the many heavy ion analyses. I'm not sure what you mean by your question, sorry.
My question is that the heavy ion data gives the better constraints on the axion particle than the proton data?
I don't think there's an equivalent analysis in the proton data, so so I couldn't say. Oh wait, sorry, yeah, it just covers a different mass regime, so it goes to lower masses. You can see the PP.
Okay, thank you. And any other questions? Okay, then thank the speaker again. Thank you. Okay, the next speaker is Sabino Longo. Sabino? Okay.
Let me just share my screen.
Okay, Sabino Longo will talk about the dark sector physics at Belle 2. Okay, let's start, please.
Do you see my slides, and do they change?
Sorry?
Do you see my slides?
Yeah, we can see.
Okay. So I'll be presenting on dark sector physics at the Belle 2 experiment. So Belle 2, we're a next generation B factory operating at the Super Keck B asymmetric electron-positron collider. Shown on the slide is a picture of our detector. So in the center here, we collide electron positrons at a square root S of about 10.6 GeV. So this corresponds to the upsilon-4S resonance. And we're targeting to integrate a 50 inverse Aldebaran data set this decade. So this is a luminosity frontier experiment, and we'll be searching for dark sectors at the luminosity frontier with a variety of methods. So we have searches looking in direct production. So we produce E plus E minus to a dark sector signature plus standard model. We also produce copious amounts of B mesons, D mesons, and taus, and we have searches looking in the decay of these particles for dark sector signatures. Then we'll also be performing precision measurements and looking for rare decays. And in this case, we can compare our measurements to the standard model as a way to see for potential hints of a dark sector. So in all three of these areas, we have analyses currently ongoing at Belle 2, exploring dark sector physics. The Belle 2 detector is a complete upgrade compared to the Belle detector. If we start at the center of the detector, we've introduced new vertexing detectors, where we start with a 2-layer pixel detector, and then this is followed by 4 layers of a double-sided silicon strip detector. With these vertexing detectors, we can use charged particles from the interaction point to get a precise reconstruction of the vertex location of the collision. We then have added a new drift chamber to the detector, which has a larger volume and smaller cells. Later in this talk, I'll show a long-lived particle search, and we'll see having a larger drift chamber volume increases our acceptance to the decays of long-lived particles. We've also had new charged particle identification detectors. So in the barrel, we use a time of propagation-based system. And then in the backward end cap, we have a Cherenkov-based system. We upgraded our thallium-doped cesium iodide calorimeter, so we've improved our timing resolution, and we've also added pulse shape discrimination as a way to identify hadronic showers. And then our final detector is the K-long muon detector system. This is a sampling-based calorimeter detector where the active material is scintillating strips in the inner barrel and end caps, and in the outer barrel, we use resistive plate counters. Now, our first collisions came in 2018, and since then, we've integrated a total data set of around just over 180 inverse femtobarns. This was achieved in such short time by operating at world record instantaneous luminosity. So Super Keck B currently holds the world record for instantaneous luminosity at 2.9 times 10 to the 34 per centimeter squared per second. Now, what's unique about this data set is we've added and included new dark sector triggers for the majority of this data set to save these unique low multiplicity final states. So if we take a look, for example, at just the rate of having particles in our acceptance from the collision, this can exceed 1 megahertz and is completely dominated by BABA and 2 photon physics. And this is too high for our DAQ system to handle. So at Belle 2, we have to have a 2-stage trigger. At level 1, it's a hardware-based trigger, and this brings the rate down to about 30 kilohertz. And then the high-level trigger is software-based and brings it down even further to 10 kilohertz. So going from 1 megahertz to 10 kilohertz, we want to save our interesting dark sector signatures, and this is where these dark sector triggers are being introduced. So one example is we have a single photon trigger, which has been operational for this entire data set. On the bottom right, this is showing the trigger efficiency of this single photon trigger, where really we're just looking for a 1 GeV photon in the calorimeter. This type of trigger was not present at Belle, and Babar recorded about 53 inverse femtobarns with this type of trigger. So this is really illustrating that we are integrating new data with these new triggers we've introduced. We've also recently added a single muon-based trigger that uses the K-long muon system. This is to target low multiplicity tau events and also low multiplicity dark sector signatures. We also do 3D track reconstruction at level 1, and this using neural networks, and this has also improved in general our trigger performance at Belle 2. So the first analysis I'll talk about is a search for an invisibly decaying Z prime boson. So in this case, the Z prime would be a vector portal mediator between the dark sector and standard model, and the Z prime can decay to dark matter particles, so these models would have a dark matter candidate. It can also impact muon D-2 and also the flavor anomalies that have been observed. So on the bottom of the slide, there's some theory references which go into more details on this. Now at Belle 2, our search, we've considered the scenario where the Z prime has a coupling only to second and third generation leptons. So in literature, this is discussed as the L nu L tau model. And we also focus where the Z prime decays primarily invisibly, so to two dark matter particles, and then it would show up as missing energy in our detector. Now at Belle 2, because we have a hermetic detector and clean electron-positron collision environment, we can have precise determination of missing energy. So this type of search is sort of ideal for the Belle 2 setting. The way we searched for it is shown by the Feynman diagram, where our collision produces a virtual photon. This then goes to two muons, and one of the muons radiates the Z prime. The Z prime then decays invisibly, showing up as missing energy. Now, this analysis actually targeted two channels. The first channel is as shown, where we produce two muons in the final state plus missing energy. The second channel looks for a lepton flavor violating case, where in this case, when the Z prime is radiated from one of the muons, it changes flavor, so we have an electron in the final state. And this gives an asymmetric final state then of a muon plus electron plus missing energy. So the search then, we select events with two tracks that are either identified as muons or identified as a muon and electron, and also missing energy in the event. And the way we search for a signal then is we look into the recoil mass computed from these two tracks. This is what's shown on the slide. On the left, this is showing the recoil mass for the dimuon search, and on the right is for the lepton flavor violating search, where we have a muon electron final state. The dominant backgrounds, one of the main backgrounds comes from tau pair events. So in this case, the taus can decay single pronged either, and then we have two muons or a muon electron, plus there's going to be missing energy from the neutrinos emitted in the tau decay. Other backgrounds come from radiative muon events, where when the photon's at low energies, it can go undetected and also mimic then missing energy. If we saw a signal, we would expect to see a very narrow peak in these distributions. However, no significant excess was observed in either search. Unfortunately, we don't see a narrow peak in the excess in the data here. So with these analyses then, we've set upper limits and exclusions. So on the left, this is showing the default search, where we look for the dimuon final state, and we set limits on the Z prime standard model coupling. So this is G prime. What we plot here is in the parameter space of the Z prime mass versus G prime. The blue shaded area is showing what Belle 2 has excluded with this search. And you can see we're approaching this muon G-2 relevant area. Something I want to highlight is the data used for this analysis was only about 0.2 inverse femtobarns, and we have almost 1,000 times that data set now. So we're looking to actually upgrade this analysis and are expecting to start to probe the muon G-2 region. In the backup slide, I have some more details on what we could reach with an updated analysis with the latest data we have. On the right, this is showing the lepton flavor violating channel, where we set model independent limits on the cross section of E plus E minus to electron muon plus missing energy. This reached limits down to 10 femtobarns, and we were the first experiment to set limits on this cross section. So these results were published in Physics Review Letters as referenced on the slide. The next analysis is a search for axion-like particles. So at GeV scale axion, these can represent a pseudoscalar portal mediator between a dark sector and standard model. Now, if the ALP-Photon coupling, so Ga gamma gamma, if this dominates, then the branching fraction to ALP to gamma gamma is also close to 100%. And this is sort of the focus of the analysis at Belle 2. The way this would show up at Belle 2 is shown by the Feynman diagram, where our collision produces, again, a virtual photon. This then goes through the ALP gamma gamma coupling to produce an ALP that then decays to two photons. So the final state would involve three photons, but actually what our detector observes can change depending on the ALP mass. And this is illustrated by the result on the left. This is from a theory reference where it's showing what the Belle 2 detector to signature would see. And this is because at high ALP mass, the two photons typically have a large opening angle, so our calorimeter can easily resolve the three photons in the event. However, as the ALP mass decreases, it starts to become highly boosted as it recoils against the photon, and this causes the two photons from the ALP decay to start to become collinear and merged in our calorimeter. And then finally, at the lowest ALP masses, the ALP becomes a long-lived particle and actually will decay outside of our detector. So in this analysis that we've performed, it focuses on the resolved region. So at higher ALP masses, where we can well resolve the three photons in our calorimeter, and also where the ALP decay is prompt. We do have analyses targeting the other regions, so merged and invisible, but just the focus of the analysis I'll discuss was in the resolved region. So in this analysis, then we select events that have 3 photons where the total invariant mass is consistent with the collision square root s. On the top right, we see an example signal event from simulation where we can see in the detector, we see these 3 photons. 2 of them are coming from the ALP decay, and then the other one is recoiling against the ALP production. And this actually gives us 2 ways we could search then for an ALP signal. We can look into the invariant mass of the 2 photons coming from the ALP decay. This should peak at the ALP mass. We can also look at the recoil mass of the photon recoiling against the ALP, and this also should peak at the ALP mass. And in this search, what we did is we actually used both these methods, depending on which one was optimized based on the ALP resolution. So on the bottom of the slide shows the results then where we see the data selected and then the Monte Carlo background expectations. On the left is showing plotting the invariant mass of the 2 photons. So here we would expect to see a very narrow peak in this distribution if we saw an ALP signal. On the right is showing the same data, but now we're plotting the recoil mass squared. It's a bit more optimal to use the recoil mass for higher ALP masses since we have better resolution in this case. Now on the left, we do see in the first bin, there is an excess in the data relative to the Monte Carlo. However, the inlay in this plot shows a zoom of only the first bin. And unfortunately, this excess is not consistent with an ALP. For an ALP signature, we'd expect a very narrow peak, even in the inlay. This would be contained in only a few bins. So in this search, then we search for a signal consistent with an ALP, spanning the mass range of 0.2 up to about 9.7 GeV. The results then are of the upper limits that we extract are shown on the left-hand side of the slide. The largest local significance we observe is at an ALP mass of 0.477 GeV. The fit is shown on the right, and this local significance corresponds to 2.8 sigma. So no significant excess was observed in this search. We then translate these limits into exclusions on the ALP mass versus ALP gamma-gamma coupling parameter space. This is what's shown on the right-hand side of the slide. You can see Belle 2, where we've covered a region which was previously covered by a recast of an old LEP analysis. So now we've sort of performed a direct search in this region and also extended a bit beyond this, where we're reaching ALP-Photon couplings now of 10 to the minus 3. The results of this analysis were published also in Physics Review Letters, as referenced on the slide.
You have 3 minutes.
The final analysis I'll talk about is the search for inelastic dark matter. This is a new analysis started at Belle 2, where it introduces an expanded dark sector. So in this case, we have 2 dark matter states introduced. The first one is a Chi-1, which is the relic dark matter, and this is stable. And then we have a Chi-2 particle, which is a long-lived particle and decays as Chi-2 back to Chi-1 plus 2 standard model fermions. The way we produce this at Belle 2 is through a vector portal coupling to the standard model, where our virtual photon mixes to a dark photon. So the Feynman diagram shows what the collision would produce, where we have an initial state radiation photon emitted. The virtual photon then mixes to a dark photon that decays to a Chi-1 and Chi-2. The Chi-1 is stable, so and escapes our detector. The Chi-2, however, is long-lived, so it propagates and then decays back to a Chi-1 plus 2 charge tracks that we can observe in the detector. So on the right, this shows a detector signature for this type of event, where we're only looking at what the detector would see. So on the bottom, we see this energy deposit in the calorimeter coming from the ISR photon. This is then approximately recoiling against this signature in our drift chamber, where we see these 2 tracks coming from a displaced vertex. This is from the Chi-2 decay. And this is actually quite a unique displaced vertex. If we look at this, we see the momentum of the 2 tracks, if we tried to add them up, would not point back to the interaction point. And this is indicating that there's actually missing energy in the displaced vertex decay. So this comes from the Chi-1 emitted and is quite a unique signature in terms of displaced vertexes. And we'll see this is used for background suppression. So the way this analysis is performed then is we use the V0 or the displaced vertex to tag the event. Immediately by having a displaced vertex in the event, this already suppresses the large majority of prompt backgrounds. The main remaining backgrounds then come from photon interactions in the material, which can mimic a displaced interaction, or from natural long-lived particles like K-shorts. Now we can actually suppress these type of events though using the topology of the displaced vertex. So as I mentioned on the previous slide, we saw that there's this sort of missing energy signature in the displaced vertex. The result on the bottom right of the slide, this is showing a variable that's measuring how much is the momentum vector of the displaced vertex pointing back to the interaction point. The more this variable, or the larger this variable is, the more two-body-like the decay is, whereas the smaller this variable is, the more three-body-like, indicating there was missing energy in the displaced vertex. So we can see for the photon conversions and for the K-short decays, where there's no missing energy, these can be well separated from the IDM type of displaced vertices where we have missing energy in the decay. Then to look for a signal, we search in the recoil mass of the ISR photon. So on the bottom left, this shows the photon center of mass energy for the ISR photon for different signal models. This is related to the dark photon mass as it's recoiling against it, so we can use this to extract a signal. So looking at the prospects for this analysis, on the left, this is showing a theory reference where it was showing the projections for what Belle 2 could reach in the plane of the Chi-1 mass versus the kinetic mixing strength. So the red is showing what was predicted for Belle 2 to reach. And on the right, this is showing a signal yield calculation where we simulated several different IDM models and computed, taking into account our reconstruction efficiencies, what type of yields do we expect for 100 inverse femtobarns. We can see we get results consistent with the theory prediction. So with this analysis, we'll be able to explore couplings from 10 to the minus 3 all the way down to 10 to the minus 4. Another thing I'll point out is on the left, we see this blue curve. This is showing the monophoton sensitivity. So at Belle 2 will, as I mentioned, will be performing a single photon search. If the Chi-2 in this case is very long-lived, it decays outside the Belle 2 detector, and this would also become a single photon search. So sort of in the region where we lose sensitivity with the displaced vertex method, it's complementary because we can also cover this with a single photon analysis that's ongoing. So coming to conclusions, the Belle 2 experiment is exploring dark sectors at the luminosity frontier. We've added new dark sector triggers to target unique low multiplicity final states. And we've published so far world-leading results on Z prime bosons and ALPs. Finally, we have a new inelastic dark matter analysis in progress that's targeting expanded dark sectors with long-lived particles. That's everything. Thank you.
Okay, thank you. Thank you very much. And any question and comments? So no comments yet. Extremely no comment, no questions in this session. Okay, Sabino, please show the Axion-Like particle part.
Which part? This one?
Next. Here. Well,
yes.
Please explain the meaning of the number of 6.85.
So yeah, this comes from actually our energy resolution in the calorimeter. So maybe I'll go to my extra slide here. So what this is showing, this result is our resolution on the ALP as a function of ALP mass. And it's showing for both the methods, so the diphoton method, or if we look in the recoil photon. So at this value of 6, just above 6, this is sort of the transition region where our resolution using the recoil method is more optimal. So if I go back to the slide where we were on, so when we look for a signal, if we're looking for an ALP mass below 6.85, we use the distribution on the left because we would have better resolution. Whereas for the higher ALP mass, we use the distribution on the right because it would have higher resolution with this variable.
Okay, thank you. And no question yet? Okay, then thank the speaker again.
Thanks.
The final speaker of this session is Lydia Brenner. Lydia, okay. Please share your slide.
Is it visible?
Okay, I can see. Please start.
Okay, great. Right, so I will talk to you about the new phasor experiment at the LHC at CERN. So this is a new experiment, which is a direct search for new physics. So the idea is to broaden the chances of finding new physics. So we have a bunch of established LHC experiments which focus mainly on heavy, strongly interacting particles. There are, of course, a large number of interesting models to test outside the focus of these large experiments. And one of those is targeted by phasor. So phasor targets light and weakly interacting particles. And this is a very low-cost experiment. The reason why it's very low cost is because we're reusing spare parts from other experiments, which I will go into more detail about in the next few slides. The total detector cost is therefore under 2 million Swiss francs. So it's built in a side tunnel, which is called TI-12. So if you have the main ring of the LHC, on one side you have the ATLAS experiment, which is one of the 4 main experiments. And in one of the service tunnels near there, you can find the phasor experiment installed. So what is the philosophy of phasor? So the idea is to exploit a high rate of light standard model particles produced in the collimated beam around the LHC beam. So there's an inelastic PP cross-section of about 0.1 barns with an N of 10 to the 16 expected at run 3. And for the very forward production, we get that theta is the QCD lambda divided by E is about a millirad. So if you look at a decay length of 100 meters, then for a mass between 10 and 100 MeV, you get that epsilon is about 10 to the minus 5. So what does that mean? If you look at the picture here on the right, you see that there's low mass of new particles with a low coupling to known particles. That's where you can find very good dark matter candidates and where also phasor is most effective. Okay, so the physics process we look at is that we target dark photons, which I will mark as A prime, as a benchmark physics process. So these are produced via kinetic mixing from, for example, the pi0 decays. It has a branching fraction of about 10 to the minus 10. So this low branching ratio is the reason why we would need a lot of pi0s. So they are detected because they decay to an E plus E minus pair in the phasor decay volume. It is also sensitive to other LLPs and the decay modes as well. So if you look at the picture here on the right, you see on the right-hand side, you see the ATLAS detector. Now the phasor location is such that it is in a direct line from the interaction point in the middle of the ATLAS detector. And that's where phasor is set up. So anything that is not charged would not bend with the LHC tunnel and would therefore go through our detector. It's about 500 meters away from there, so it has a lot of time before it gets there. And in this way, we're hoping to find this A prime decaying to an E plus E minus pair. I also put here a reference to the physics letter, physics review, where the physics potential is discussed in more detail. Okay, so let's look at the detector overview. So all the way at the front of the detector, there's a part of the detector which we call the phasor nu. This is the neutrino detector. This is at number 1. At number 2, you can see the Vito scintillators. Then you see a dipole magnet, which is about 0.6 Tesla. Then we have tracker stations. There's 3 tracker stations indicated with the number 4. Then we have a scintillator for the precise timing, and a scintillator based pre-shower, and finally a calorimeter. So the tracker are made from spare silicon strip detectors, which are called SCT modules, which were left over from the ATLAS experiment. So each module that was received was tested, and the best quality modules were used. So we have 3 tracker stations. Each of these stations consists of 3 layers, and each layer consists of 8 modules, which means we have 72 modules with of the order of 10 to the 5 channels in total. So what we did is we had an extensive testing on the surface, which then showed the expected performance, which means that we have about 25 micrometer resolution and less than 0.1% defective strips. In the bottom, you can see again where the tracker stations can be found inside the detector. So then we have the scintillators. The scintillators have a trigger capabilities spread over 3 scintillator stations. It has a high efficiency veto stations for vetoing charged particles, since that's not what we're looking for. And the efficiency is generally measured to be larger than 99.995% for a single layer. So this efficiency is calculated based on cosmic data. And we used a tracker station and 3 scintillators to measure this efficiency. So what we do for that is we require a straight track from the tracker to be able to count as an event for this measurement. So the calorimeters are made from 4 calorimeter modules that from the LHCb outer ecal. So again, they were leftover spare parts from now a different experiment. So they are read out using the PMTs from LHCb with a custom voltage divider base. It consists of 66 layers of lead scintillator with 25 radiation lengths in total. They are calibrated using LED calibration, and the energy resolution is about 1% for a TeV deposits. So, as I mentioned at the very beginning of the whole experiment, there's a part which we call phasor nu. So neutrinos are obviously produced in abundance in the standard model. So the goal is to also measure these neutrino cross sections in the collider energy range, which is about 100 GeV to a few TeV. So this additional detector at the front of phasor is about 1.1 meter long, and it consists of about 1 ton of tungsten emulsion stack. So in the plot here, you can see that the physics process that we try to measure. So you would have for example, pi plus, which decays to a muon and a muon neutrino. This muon neutrino then propagates through all of the rock and line of sight for phasor, and then further decays, which we can then measure inside the phasor nu detector. So a huge number of neutrinos are produced in LHC collisions, in, for example, hadron decays, and then transfers to the phasor location, covering an unexplored neutrino energy regime. So the primary physics goal here is to measure the cross-section at a high energy. So here you can see the projected results on the left for the electron neutrino, in the middle for the muon neutrino, and on the right for the tau neutrino. So actually, after a small update on our detector, this middle plot is not quite accurate anymore, because with our new upgrade, we should actually be able to measure the neutrino and the anti-muon neutrino cross-section separately, which isn't shown yet in this plot. So the most important uncertainty for this measurement comes from the neutrino production. So we built an approximately 30 kilogram prototype, which was installed in the phasor location, which collected about 4 weeks of collision data in 2018. So in this time, it was exposed to 12 inverse femtobarn of data. We then used a BT classifier to classify between the signal and the background events. Now, the background consists of neutral hadrons produced from muon interactions in the rock in front of the detector. So here at the bottom, you can see a picture of this prototype. So you can see that it's about 10 centimeter high, and it's placed exactly in the beam collision axis before the rest of the experiment was installed. So from this, we determined 6 neutrino candidates where we actually expected 3.3 events, which gave us a 2.7 sigma significance of rejecting the no neutrino hypothesis. So what you see here is an event display of 2 neutral vertices in the YZ projection. So on the left, you can see this longitudinal to the beam direction. And on the right, you can see it in the view of the transfers to the beam direction. So more details on these first neutrino interaction candidates at the LHC can be found on the archive link that is given here, which has also been submitted for publication. Okay, so then we get to the phasor installation. So the whole detector was successfully installed in the TI-12 tunnel in March, and since then has been taking cosmic data. So here you see two pictures of the installation process. So on the left, you see the phaser detector. These blue parts are the magnets, and in between the magnets, you can see the tracker stations, for example. And on the right here, you can see the phaser location compared to the LHC beam. So you see the phaser cavern, where someone is standing in front of it to give you a bit of an idea of the size. And on the right, you see the LHC beam going around. So we did a first cosmic run with full detector on March 23rd. And it has been continuously running to test the remote operations and monitoring. We've managed successful triggers with the scintillator coincidence. The tracker performance is matching the performance of the surface test. And we have automated the data quality and monitoring. So what you can see here on the right, if you is the phase space that phaser will cover. So if you look at the yellow area, which says 150 inverse femtobarn, this is about the area we will cover during run 3 of the LHC. So you can see that this really covers, compared to, for example, Belle 2, which we've just heard some stuff about, a very different phase space. Okay, so let's say a little bit more about how these cosmics runs work. So for example, we have a bunch of single station tracks. So what that means is it goes through 3 layers of station and is triggered by a nearby scintillator. The rate for that is about 1 event per minute. So you can see here on the right a small diagram of what this looks like. So each layer has 2 sides of it. To be able to call it a hit, it has to go through the top and the bottom of each layer basically simultaneously. And you can see here, this is an actual real cosmic event of the track going through one of those layers, one of those stations, so 3 layers. Then we have some double station tracks. For this, we have a couple of events per day, which go through in a nice line with the scintillator still through 2 of these stations. Then we have some triple station tracks. So these are expected to be very rare. And the first candidate was actually just observed. So here, you can see some of the double station tracks, one double station track event. An example for this. So you see that in the red line is the trigger of the scintillator. Then you have these 3 green blocks, which are the 3 tracker stations, where you can see the nice track going through these stations. And then going outside of the detector regime for the 3rd station. Okay, so that brings me already to my summary. So most importantly, phaser has now been installed in the LHC tunnel, and the initial commissioning in the tunnel has gone smoothly. The first physics results from the neutrino pilot run have been submitted for publication, and we're looking forward to our first results from LHC collisions of run 3. And of course, there's thanks to all of the foundations and CERN for supporting us. Thank you.
Thank you. Thank you for the interesting talk. Okay, so final talk finished. And any question and comments? Yeah, there is questions. Could you read the questions from the chatting?
Let me try. It doesn't show me the chat anymore.
Let me read the questions. In the 6 neutrino candidate events of the 2018 run, could you distinguish the neutrino flavors?
That is a good question. No, at this stage we couldn't. This was also a much smaller setup. And actually our detecting software wasn't quite as developed as it is now. So for this, we only say that we can say there were neutrino candidates, and we can show that the no neutrino option is not a possibility, but not which flavor the neutrinos were. But for the run 3 one, we will definitely be able to do that.
Okay, any other questions? Okay, let me ask one question. The phasor neutrino is a very small detector, but the phasor is a much bigger detector, right?
Yeah, so phasor nu is just a small part of the full
yeah.
full detector.
So for the phasor, do you need any more civil engineering, more new tunnel?
So no. So what we are using is an old SPS surface tunnel. And then for that, we had to dig a small trench to be able to have it completely level with the interaction point of ATLAS, which is about 30 centimeters deep. But this was already made, and it's now fully installed. So now we don't need any further civil engineering.
But the size of the phasor is a few 10 meters, right?
It's about 5 meters.
5 meters. 5 meters.
Yeah, maybe 6 with the neutrino part added to it.
Okay, thank you. And any other more questions? Okay, if not, we thank the speaker again. Okay. Yeah, then, well, we finished earlier. Now we have 10 minutes earlier. Okay, then we close this session and we thank all the speakers again and thank all the audiences. Thank you.